Do you even squat? Analysis on optimum squat posture. Hi, we're Chad, Sally, and Susan here to present the topic of optimal squat posture prepared for MTE204 Phase 2. The squat is an exercise where a person carries weight above their shoulder and bends their knees to go down and extend their knees to go up. It not only works out your legs, but your back muscles as well. It is the perfect workout plan for those people who wants to get jacked. However, if not done right, it can bring some serious consequences with the injuries. In this project, we attempted to numerically solve what the best posture is at the lowest point of squat in order to minimize the damage in the joints, as well as explore the difference between unrestricted squats and restricted squats.
Our goal is to find the best squat form. Even though the squat appears to be relatively straightforward, there are actually many factors which determine how your body moves and responds. For our model, simplifications were made. First, we will only analyze the problem statically at the bottom of the squat. There is no inertia considered. The human body is very complex without the interaction between muscles, ligaments, joints, and so on. In this model, we are simplifying the human body to a series of straight linkages connected by pin joints. We will model the back as a straight line connected from the hip to the bar. In reality, the curve of the spine and rotation of the hips will vary the amount of stresses on the back. Also, we are considering the problem in 2 dimensions on the sagittal plane. Furthermore, we are not accounting for the body's density or mass moment of inertia. We also estimated the proportions of the human body. With all these simplifications considered, our actual aim is to solve for the ankle, knee, and hip angles, which will result in the least torque on the joints at the bottom of the squat. This is a frame taken from the video where Zach is at the bottom of the squat. The angles shown in yellow are the angles we want to optimize to obtain the lowest torque on the joints. We are modeling only the body below the applied weight. The back, upper leg, lower leg, and foot are modeled by the blue lines. Dimensions are taken from this frame to approximate the ratios of the limbs. The red lines are the distance vectors R. They go from the ankle to the applied load as well as the knee to the applied load. These vectors are used to find the moments at each joint.
Our group decided to use MATLAB to simulate our process. So these are the pre-processing where the forces and the lengths and the dimensions are defined. This is the main loop. Each of the angles loop from 55 degrees to 89.5 degrees because we found that it would never go over 90 degrees and it would never go below 55 degrees when you're squatting, especially at the very end. So these seemed like reasonable values. There are some geometrical definitions that we had to make. This code right here is to find the R vector in order to find the moment to do cross product. So R hip is the R vector from the hip to the load. R knee is from the knee to the load, and ankle from the ankle to the load. There are some positions that had to be defined in order to solve some math. And finally, and really importantly, the centroid of each posture at each iteration had to be found using the centroid code. There's some more R vectors that had to be calculated in order to account for the moment. So now, calculation of moments. Moment is defined by R cross F. So we have the R of the hip, which is the hip joint to the load and the load itself. Those are crossed to get one part of the moment. And additionally, the R vector from the hip to the centroid had to be crossed with the mass of the torso that's exerted from the centroid in order to calculate the total amount of moment. And that is done with both knee and the ankle. And then moment calculation for each reaction forces are done. This is very important because one of our criterias is that the person cannot tip over either forward or backwards. Therefore, if the moment that is created about the centroid of that truss is greater than the moment that's created by either the reaction force on the toe or the heel, that means that the person will tip over either way. Therefore, we have this if statement that says if the moment that's created by the load is minus moment that's created by the reaction on the toe is greater than 0, or if the load is bigger than the reaction from the heel, then the loop actually just continues because we consider that iteration as a failed posture. If, however, the angles and the posture does not go through this restriction, which means the person does not tip over, then the moment is nicely vectorized, and then the norm of the moment is found, and then the angle is also recorded. If the norm of the best moment that's right now is greater than the norm that's calculated in this iteration, that means that the norm that's calculated currently is the best moment, because we're trying to reduce the magnitude of the norm. Therefore, the best values are updated here, and the posture is plotted. And at the end, the best posture and the best centroid is modeled as well as with some data. So if we were to run this script and this figure illustrates all the possible postures that go through this condition of if norm best is greater than norm current. So these all represent postures that reduces the norm from the previous best posture. And if we let it continue to run, which should be over soon. Oh, and these are the centroid values that are updated of the posture. At the very end, the best one is updated and the angles are given. So 55 degrees is this one, 55 degrees, and 73 degrees is the angle of this orange line from the horizontal. The best moments are 121 on the hip, 127 on the knee, and 16 on the ankle. Now, just to check the norm, if we type in norm underscore best moment, we can see that the norm is 176.9927, and that's the best that the posture can distribute the loading. Just as an added bonus, if we were to comment this out and instead plot the positions that fail to meet the criteria, it is possible to see more of the drastic positions that are made. So if you can imagine, these postures are all postures where if the load was applied on the tip of this vector, they would tip over, which fails to meet the criteria. This is the main squat code that we have written, and for more details, please refer to the actual code that's on the GitHub, which is commented pretty well.
Next, we'll be talking about how we optimize the position of the squat. We wanted to minimize the torques at the hip, knee, and ankle with respect to the angles at each joint. And we wanted to optimize the function with respect to one number instead of all three moments at the same time. That is, we wanted it to be a scalar valued function, so we optimized with respect to the Euclidean norm of the torques. And to optimize, we used a MATLAB function called fminsearch, which attempts to find the minimum of the input function. To verify the solution given by fminsearch, we also computed the squat position using a series of 3 for loops to iterate through every possible angle. fminsearch uses the Nelder-Mead algorithm, which is a very popular form of derivative-free optimization. Derivative-free optimization, as its name suggests, means that the function is not minimized through the derivative or the gradient. This is good because we did not need to write an explicit function that could be differentiated to be optimized. We simply had to define a function that calculated the norm of the torques given a set of input angles. And the Nelder-Mead algorithm uses something else called the simplex method. And in a nutshell, the simplex method operates on the principle that the optimal value of... And here I'm running fminsearch. As you can see, the angles it gives are 55, 55, and 72.6916. As the for loops iterated through the angles by an increment of 1 degree at a time, the maximum accuracy it can achieve is within 1 degree. We can see that the brute force approach with the 3 for loops and fminsearch's solutions are within 1 degree of each other. The Nelder-Mead algorithm's iterations. And as it's iterating with respect to 2 variables, that is 2 dimensions, each simplex is a triangle, and you can see it converging towards the optimal point of the function. Some considerations are that the Nelder-Mead algorithm may converge to a non-stationary point, that is to say, a point that's not a minimum of the function. This is a famous counterexample that shows the non-convergence of the Nelder-Mead algorithm. In this function, the algorithm converges towards 0, 0, as you can see by the triangles, even though this is not even a local minimum. It can also be very slow to converge when there are many dimensions. But these weren't a problem for us because we only optimized with respect to 3 variables, the angle at the hip, knee, and ankle. In addition, we verified fmin search's solution by iterating through all of the possible angles with 3 for loops, which gave the same solution.
The script that was ran and the simulation that was ran was nice and all, and the result looked pretty decent, but how do we exactly validate it? Unfortunately, our group was not able to find any research paper that specifically did the same topic that we did. Therefore, what we had to do was we took our main idea and the main script and we wrote another one in order to validate with a paper. The paper that we decided to validate on is called Effective Knee Position on Hip and Knee Torques During the Barbell Squat. This paper research explores the difference between restricted squat, which the knee is not able to go past the toes, versus unrestricted squat, where the knee is able to go past the toes. Their result was this. For unrestricted squats, their knee torque was greater than their hip torque. However, for the restricted squats, their knee torque was less than the hip torque. And we attempted to see if our script was able to recreate this kind of result. Because at the end of the day, as long as our math and assumptions work out for one of the papers, we can safely assume that the research and simulation that we're doing on our topic would be somewhat correct. So we have a very similar code as before, except in order to generalize things, because unfortunately this paper did not provide any dimensions for the subject whatsoever and the mass. So therefore we had to keep it very general. Tibia was now calculated using these kind of relationships, which we found on this paper called Anthropometric Data, which is from University of Rhode Island. And using these values, we calculated the new values of tibia, femur, spine, and foot dimensions. And the applied load was kept the same. The load itself was also not given in the paper that we're trying to look for, but it does not matter because as long as we can draw the same conclusion, we can safely validate our results. So these variables are set up initially, and with the loop, it does exactly the same thing, except the main calculations are these. If the point of the knee, so if the x position of the knee is less than x position of the toes, which means it is a restricted squat, all of these restricted variables are updated. On the other side, if the position of the knee goes past the toes, then all the variables of the unrestricted are updated. At the end, the mean of the moment and the mean standard deviation of the moment of the hip and the knee are calculated for both restricted and unrestricted. The angles are commented out because the angles are very sensitive to the dimensions, and we cannot say that our dimensions are very similar to their subject's dimension. So the angles were different, but the focus is more on the torque and which one is better and how can we draw the same conclusion. So if we run the script, it's running. So while the script is running, the knee torque for unrestricted squat was greater than the hip torque by 150 divided by 28, which is around 5.35. For the restricted squat, the knee torque was less than the hip torque, and to calculate how much, we do 302 divided by 117, equals to around 2.58 times greater, the hip torque. Now our result is shown, and the moment restricted. So the first value that gets shown is the hip, and then the third is the knee for the mean. And the same goes with unrestricted. So for the restricted, the hip torque was around 53.5625. And the knee torque was, the magnitude only is 20.6672. Dividing the hip torque, 5625 divided by 20.6672, we can see that the hip torque was greater than the knee torque by around 2.59, factor of 2.59. Whereas previously in this paper, the restricted squat, the hip torque was greater than the knee torque by around 2.58. So therefore, the restricted squat is validated. Secondly, for the moment unrestricted, we can do the same calculation. So just checking, our knee torque is greater than the hip torque. And by how much? We'll check it out right now. 62.7194 divided by 11.3947, which we get 5.5. Whereas in the paper, the knee torque was greater than the hip torque by 5.35%. So you can see that the results were very close. And the same conclusion can be drawn compared to this paper versus my script. The project explored the surface of a broader field of academia called biomechanics, which has a lot of implications in the science and engineering community. With this specific example of squat, the field of sports engineering can actually benefit the most. For example, one of the papers that we found titled A 3D Human-Machine Integrated Design and Analysis Framework for Squat Exercises with the Smith Machine, which we linked in the video, researched about the design process of a Smith machine. Their approach was to find different postures and their effects on the human body while squatting with an aid of a Smith machine. Additionally, this could be used in the field of prosthetic legs and exoskeleton technology to minimize the torques that are applied by the motors when a person has to squat. Finally, for the engineers that regularly goes to the gym, finding the optimal posture at the lowest point of squat will help you minimize the risk of injury or damage on the legs, hips, and lower back while doing squats. In conclusion, with the dimensions that we worked with, the optimum squat position at the lowest point of the squat is 55 degrees from the spine to the thigh, 55 degrees from the thigh to the shin, and 73 degrees from the shin to the horizontal. Also, in order to minimize the knee torque, restricted squat is recommended, whereas if you want to reduce the moment about the hip, the unrestricted squat is recommended.